This is a basic relaxation oscillator. It's a very interesting op-amp circuit because it has no input, but it has an output. It's also interesting for two other reasons. One is it introduces the idea of positive feedback. That's to say the output goes back to the non-inverting input of the op-amp. Normally this is not something you'd want to do. But in our case, it adds a very interesting feature to the circuit. The second interesting point is that unlike most op-amp circuits that are operating linearly, these two inputs here, the inverting and non-inverting inputs voltages, are the same. This circuit is not going to be operating linearly, and these two voltages will not be the same. So let's see how this works. When we power up the circuit, it is possible for the voltage at the output and these two inputs over here to be exactly zero, and the circuit's happy with that, and it'd be very stable. But what happens is that because of electrical noise anywhere in the circuit or imbalance, the very high gain associated with the two inputs causes the output to latch to either the positive or the negative supply rail. So let's say that our op-amp is running on plus VCC, some positive voltage, and is also running on a negative VCC rail. So we're going to start off by taking a look at making little sketches of what happens at the around this circuit. And so we'll start off at time equals 0. And we'll look first of all at what happens at the output. Initially what happens is we turn on the circuit, the output will latch either positive or negative to the maximum. So we'll just simply say, well, it latches high. And it's perfectly happy to stay there for forever, normally. So this is VO. We'll just have this line as being VO. And it goes to the value of VCC. Now you'll notice that the voltage at the non-inverting input is simply going to be a fraction of its output because it's affected by this voltage divider. So the output, or the input rather here, is going to immediately snap up to some value. We'll just call that V reference, some V reference value. And that V reference value is simply equal to the output voltage, VCC, times the voltage divider action of these two resistors. So it's R1 over R1 plus R2. So that's what this voltage will immediately snap up to. Now the capacitor starts off, let's say, at 0 as well. And because this snaps to the positive supply voltage, current will begin to flow like that. The capacitor will begin to charge. And so the capacitor is going to want to charge to this value, which is VCC. So it's going to want to get up there. It's going to want to charge all the way up to VCC. But you notice what happens here. As the inverting input is charging, at some point it's going to exceed the value on the non-inverting input, right here. And what this is going to do is that because these two polarities now pass each other, this output is going to flip. So this capacitor will charge, it will get only as far as the same value on the non-inverting input, and then all of a sudden the output voltage will snap down to minus VCC. So that's where VO goes. VO snaps down there. And of course, the voltage at the non-inverting input is simply the voltage divider. It's going to drop, and it's going to drop down to minus V reference. Because the voltage here is changed, polarity, become negative, this capacitor will start now to discharge this resistor. And so it's going to want to discharge from this value going to want to discharge, and it wants to discharge all the way down to minus VCC, the voltage over here. But of course, as you can see, it falls, it falls, it falls, and then at some point, the voltage here falls below the voltage here. There it is. And because the polarity in these two inputs is flipped, the output will flip. What happens is the output voltage will now snap back up. And the voltage at the non-inverting input will come up. And then, of course, the capacitor wants to now charge to VCC again. But it's not going to make it, it's only going to make it this far to where the two inputs here are the same, and then the whole process repeats itself. So notice what we have here is we have a circuit that is constantly changing states. So it's an oscillator. The output will vary between plus and minus VCC. Actually, in a real op-amp circuit, it'll be a little bit less than that because the output of an op-amp can't go all the way to the supply. It can go as high as 1.5 volts of it. So it's actually going to go to VCC minus about 1.5 volts. And over here, it's also going to be the same thing. It's going to try to go to minus VCC, but it's actually going to go to that plus about 1.5 volts, something like that. Notice that the voltage here will be a completely nice square wave, symmetrical square wave. The voltage at this point is going to be the charging of a capacitor. So it's going to be not quite a ramp. It's going to have a curve in it. It's going to have a curve in it. So we can use this to make a basic sawtooth waveform, but it's not a really good sawtooth waveform. Now we'd like to find out or analyze how the component values R1 and R2 and R and C, how they affect this waveform. Obviously, the value of these two resistors affects the voltage in the reference here. That affects the point at which the circuit will flip states. So that has some influence as to whether it's going to change states over here or over here. So it's going to have a slight change on its frequency of operation. And likewise, there's this RC time constant over here, which influences the rate at which this thing is running. So let's see how we can go about analyzing and the circuit to find out exactly how fast it will run. The purpose of a relaxation oscillator is to create a signal of a specific frequency. That frequency is the inverse of this period here, time. So we'd like to find a relationship between time and these components, RC and R1, R2. To do that, we have to review the basic charge of a capacitor. And the way a capacitor charges is like this. We have a voltage source here, the switch, RC. The capacitor starts off with an initial charge of 0. When we throw the switch, the capacitor charges exponentially like this. And the equation which describes that is simply voltage in a capacitor is equal to V, the input voltage, times 1 minus e to the minus t over RC. Now there is one problem with this equation in our particular application, and that is that this equation is valid when there is no initial charge in the capacitor. But as you can see from the circuit, the capacitor does charge from an initial value. It's minus Vref. So we have to somehow take into account the initial charge in the capacitor at the beginning of this cycle. So how can we do that? Well, it's actually relatively straightforward. We'll just expand this expression for a moment. And we have voltage in capacitor equal to V minus VE to the minus T over RC. Now, you might think that the easiest thing to do is just simply add an initial voltage into this equation. Well, let's just try it and see what happens. If we're to add voltage initial, then at time equals 0, this expression over here equals 1. So we end up with V minus V, which is 0, plus V initial. And so it seems that the capacitor will charge at the beginning from initial value. The problem occurs is what happens as time goes on to infinity. Then we notice that as t goes to infinity, this expression over here goes to 0, and so the final charge of the capacitor will be the input voltage V plus the initial voltage. Well, that can't be. The final value, regardless of what the initial value here is, must be the input voltage. So this has to go to 0 as time goes to infinity. And the way we do that is exactly the way it happens right here. We just multiply this by e to the minus t over RC. And now what happens is this equation starts t equals 0 with the initial in the capacitor, and at t equals infinity it ends up with the input voltage V on the capacitor. So we'll call this equation Vc with a plus, an initial charge. And we can pull the e to the minus t over RC terms out. So we'll just do that. And we'll reverse these two so that we're adding here. So this is going to be V initial minus V times e to the minus t over RC. And this is the equation which describes the charge of a capacitor when it starts off with some sort of initial value, non-zero value. Notice that the initial value is 0, then this equation is exactly as we had in the beginning, so no change is made. So now we're going to apply this formula to our circuit. So now let's apply this equation to our circumstance. So what we're interested in doing is finding this time period here, and we know the voltage that the capacitor starts off at, and we know the voltage that it ends at, and we know the voltage that it wants to try and achieve, but it never does. So we can put all those factors into this equation here. So this represents here the final value when we want the time to stop, and that is simply V ref. And that's going to be equal to the voltage that the capacitor wants to rise to. It wants to rise to VCC. Plus the initial voltage over here, which is minus V ref. Minus VCC times e to the minus. And now we're interested in this period here, this length of time. So that's going to be t over 2 divided by RC. T divided by 2 RC. So this represents the equation that describes what happens during this period. And what we're interested in doing is solving the equation for t. So let's do that. We can just move this over to the other side. So we have V ref minus VCC is equal to minus V ref minus VCC, the whole thing, times e to the minus t over 2 RC. And of course we'd like to get this on the left hand side, so we'll just flip these all over. So over the left hand side we're going to have V ref plus VCC times e to the minus t divided by 2 RC is equal to, and flipping this over we're going to get VCC minus V ref. So you notice that in flipping left and right I just simply conserved the positive signs as many as possible. Okay, so now we want to extract this term. So e to the power of minus t over 2 RC is equal to this expression, VCC minus V ref, divided by VCC plus V ref. Now, at this point, you may recall that V reference is made up of two components. You can just simply say recall Vref is equal to R1 over R1 plus R2 times VCC. Now, in most of the literature, this fraction over here, R1 over R1 plus R2, is referred to as the feedback factor. And so in a lot of literature, this is simplified to simply letting it equal to B. So we'll just do that. We'll just simply say let R1 over R1 plus R2 equal B, the feedback factor. And so therefore we can write that V reference is equal to B, the feedback factor, times VCC. So now let's plug this expression into here. And notice what we get. We get e to the minus t divided by 2rc is equal to VCC minus B times VCC divided by VCC plus B divided by VCC. And right off the bat, you notice that VCC cancels out completely. So this reduces down to simply 1 minus B over 1 plus B. So that's pretty straightforward. What's very interesting to note is now that as we're going to solve for the time and ultimately the frequency, the voltage on the op-amp, the power supply that it operates it, has no effect whatsoever. The frequency is determined only by the ratio of the feedback factor R1 and R2. So now let's go and solve this expression. So to do that, we're going to take the natural log of this side, and so that gives us minus t over 2rc, and we take the natural log of this side is equal to the natural log ln 1 minus b over 1 plus b. And of course now we can solve for t. T is simply equal to minus 2rc, the natural log of 1 minus b over 1 plus b. Now at this point, alarm bells should be ringing in your head because it looks like we have negative time here. And that can't be. So how do we resolve this dilemma? Well, interestingly enough, when we take a look at this expression over here, 1 minus b over 1 plus b, this number is, by inspection, less than 1. And what is the natural log of any number less than 1? Well, it is negative. So notice we have a negative times a negative, so the whole thing's going to turn out to be positive anyway. So let's write this in such a way that we can legitimately get rid of this negative sign. The simplest way to get rid of this negative in this expression is to recognize that by flipping this fraction upside down, this negative disappears. Let's go back for a moment and see this in action. If we take a look at the natural log of 1/3, you'll find that that's equal to minus 1.099, so about 1.1. The natural log of 3 is plus 1.099, about 1.1. So let's do that. Let's flip this fraction upside down and this negative will disappear. So t is equal to plus 2rc, the natural log of 1 plus b divided by 1 minus b. Now, we can make further simplifications by taking advantage of this fact right here. Notice that the natural log of 3 is about 1.1. So if we could make this number over here equal 3, it would really simplify this expression. So why don't we just do that? Let's just simply let R1 equal R2. If we do that, notice what happens. Then B, the feedback factor, equals R over R plus R is equal to 1/2. And plugging that into here, we notice that 1 plus 1/2 divided by 1 minus 1/2 is equal to 3. So that's kind of convenient. So let's do that. Let's just make life really simple for ourselves in designing the circuit and have R1 equal R2. And then this equation reduces even further to T is equal to this expression, the natural log of 3 now becomes simply 1.1. 1.1 times 2 is equal to 2.2 RC. And there we have it. The basic expression for the period if R1 is equal to R2. And the frequency of oscillation, which is ultimately what we're trying to determine, that's to say we know what the frequency is because we're designing an oscillator for a frequency. When I pick the components to get that frequency, the frequency is simply 1 over T, or 1 over 2.2 RC. And there it is. There's the basic design equation for an op-amp based relaxation oscillator.